Section 1.7 Complex Numbers. So we're going to study a new class of numbers in this section, and we will be using them later on in this course. So let's first talk about why we need complex numbers. Okay, so if you recall, when we did this section on radicals, okay, we did problems like this. We were given something like this: square root of, let's say, 144. And we wanted to find that. What were we looking for? We were looking for some number whose square, since we're talking about a square root, is equal to 144. And in this case, we know that 12 square is 144, so the answer was 12. Okay. If we had another example like this, we had, let's say we wanted to find the cube root of something, the square root of minus 9. So what did we want to do? We wanted to find a number whose square is negative 9. Okay, so we're looking for a number whose square is negative 9. And if you think about it, if I take any number and square it, we always end up with a positive number. So there's no way I can take a number and square it and get a negative number. I should point out there's no real number that works that way. Okay, so there's no real number. Okay. Whose square is going to be a negative number. So this is not possible, because every time we take a real number and we square it, we get a positive number. But what if we want to be able to do this? We want to be able to take square root of negative numbers. What do? Well, to get around it, we have to create a whole new class of numbers called complex numbers. So far, from intermediate or basic algebra, we have something called real numbers. Real numbers are broken down into rational numbers and then irrationals. Okay, and then rational numbers are broken down into integers, which are further broken down into natural numbers. Okay, so, and these symbols, I should really use the symbols for them. This is the symbol for integer, and then for natural number. So that is how the numbers are classified. That's your number system. Real numbers can be broken down into two categories. Rational basically means fraction. We've talked about that many times in this class. And then the rational numbers are broken down into integers, which are whole numbers, like 2, 3, minus 4, minus 5, 0. And natural numbers are basically just positive integers, okay, not including 0. Now, if you just work with real numbers, then we cannot do this, because we cannot take square root of negative numbers, because there's no real number that works that way, because that real number squared gives us a positive number. Okay, so we have to create a whole new class of numbers above the, let me just do it this way, above the real numbers, called complex numbers. So a complex number can be broken down into real numbers and so on. Okay, so that's what we want to take a look at. Okay, the complex number is made up of a real part and a imaginary part, which we'll talk about in a second. Okay, but that's what we want to be able to do. So let's go ahead and define that, because the whole reason for studying complex numbers is to be able to take square root of negative numbers, or to be able to take even roots of negative numbers. Okay, keep in mind, if you were taking cube root of negative numbers, that's okay. Like if I had cube root of negative 8, what do we want? We want some number whose cube is negative 8. So you take negative 2 cubed is negative 8, so this number is negative 2. So if the index is odd, that's okay, because we can take cube root, fifth root, seventh root of negative numbers. We cannot take even roots of negative numbers. For example, the fourth root of negative 16. What is that? I want to take some number to the fourth power and get negative 16. Anytime I take a number to the fourth power, any number, I'm going to end up with a positive number, any real number. Okay, we're going to end up with a positive number, so there's no way we can get a negative number back. So that tells me that there's no real number that works that way. Okay, so you can see the reasoning why we need complex numbers is because we want to be able to take square roots, fourth roots, sixth roots of negative numbers. So let's go ahead and define complex numbers. a complex number has the form a plus bi. So the complex number always has this form a plus bi, where a and b are real numbers, and this is called the real part, and this term with the I is called the imaginary part. Where a and b are real numbers, they're just your regular real numbers, and I was your special quantity here. I is equal to square root of -1. That's how we defined I. Okay, I is called square root of -1. Okay, so now let's take a look at how that's going to help us take care of negative radicals and things, negative square root of negative numbers. Okay, so that way we can justify them. Okay, but before I go there, I just want you to remember complex numbers are always written in this form, where the real part and the imaginary part are separate. This is a real part, this is the imaginary part. Okay, so keep that in mind for later in this section when I have to point that out to you again. Okay, so let's take a look at some examples first, and then we'll take a look at how that helps us with negative square roots. So here's some examples of complex numbers. I could have -2 plus 5i. That's a complex number. Here's another example, minus 4i. So these are just some basic examples of complex numbers. Okay. You could also have 3 minus 2i, and so on. So these are all examples of complex numbers. Okay. All right. I just want you to see how we can take care of negative radicals. So note, I want to point out two things. One, so now let's take a look at square root of -9 that we were talking about earlier. From the properties of radicals, we know that square root of -9 can be written as 9 times square root of -1, because 9 times -1 is -9. And then we know that square root of 9 is 3, and we just define square root of -1 to be I. So that's how we can write square root of -9 now. We can write it as 3i. Similarly, if we have the fourth root of -16, I can write that as, we can break it down into let's do square root of -16, be easier. So we can break it down into square root of 16 times, we have, square root of 16 times square root of -1. Okay, so we end up with square root of 16 is 4 and square root of I is -1. Now let's go back to the problem that I was talking about earlier, which was the fourth root of -16. So we get square root of 16, fourth root, times the fourth root of -1. But what is the fourth root of -1? So we don't know that. So this one's a little bit harder to do, but it will still result in complex numbers. It's just the way we did these two examples, we cannot do this one. We have to actually change it to polar form and do it. Polar form of complex numbers and do it. And that's something you would learn in a trig class or in a complex analysis classes, something like that. But that is something you can do it. Actually, if you were to do that, you would end up with that the fourth root of 16 actually happens to be square root of 2 plus square root of 2i minus square root of 2 plus square root of 2i minus square root of 2 minus square root of 2i, and we have square root of 2 minus square root of 2i. So that is the fourth root of -16. So that's a little bit more complicated than just doing the square roots, but for us this is what we need to worry about. Okay, So that is something we can do with complex numbers now. That is something complex numbers let us do, take square root of negative numbers now. Okay, we're talking about square roots. Alright, so now that we know what a complex number is, we know how we can utilize them. Let's take a look at some of the operations we can perform on complex numbers. Oops, before I do that, I told you there are two notes I wanted to make. This is my first note, and here's my second note. We defined square root of minus 1 as I. Correct? That's how we defined that as. Let me write it backwards. I is equal to square root of minus 1. So if I square both sides, I get I squared is equal to minus 1. So these are the two things you should always know about complex numbers. I is equal to square root of minus 1. We used that to write these radicals a minute ago. And then I squared is equal to minus 1. That's because sometimes some textbooks might ask you problems like this. They would ask you find I raised to 20. What is that? Well, since these are the only two I values we know, we need to utilize those. So let's be a little bit creative. 20 is an even number, so I can maybe write it as this: I raised to 2 raised to 10. Because 2 times 10 is 20 using exponential property. And then what is I squared? I squared is minus 1 raised to 10. Any number raised to an even, any negative number raised to an even power is always a positive number, so we get just 1. Okay, so you multiply negative 1 10 times, you get 1. So you can see that once we know these two values of I, we can pretty much calculate any I raised to any power. So let's take a look at another one. I raised to 53. Okay, now that's not an even number, but we can be creative with it. I can write it as I raised to 52 times I raised to 1. Because since the base are the same, I can add those exponents to get 53. And then I can write I raised to 52 as I squared raised to 2 times what is 52? It'll be 46 times I. Okay, I'll do it on the side here. Then I squared is minus 1. We talked about that. Raised to 46 times I. Any number, a negative number raised to an even power is positive, and any 1 raised to any power is just 1. So we just get 1 times I, which is I. So I raised to 53 is just I. So as you can see, now we can find a lot of different values of I. You just have to use these ideas. You just basically want to break the exponent into, write the exponent, as some power of I squared. Okay, so if it's an even exponent, that's easy to do. But if it's an odd exponent, you first have to break it up into even and 1, and then write the even exponent as I squared. Okay, here's one more example of that just to drive home the point. Let's say if you have I raised to 14, let's do 15. Okay, since it's an odd exponent, I can break it into even and 1, since we want to somehow use write the power as I squared. You can see that. So now the even one can be written as I squared raised to 7, because 2 times 7 is 14 times I. So we get I squared is minus 1. We just found that out here. Raised to 7 times I. Any negative number raised to an odd power is negative, and 1 raised to any power is just 1. So we get minus 1 times I. So we just get negative I. So I raised to 15 is negative I. Alright. Okay, so let's move on to the second topic that we want to cover in this section, which is on what can we do with complex numbers, operations on complex numbers. So we can start by adding and subtracting complex numbers. Adding and subtracting complex numbers is exactly the same as adding and subtracting polynomials. It's absolutely no difference. Instead of x in a polynomial that we normally use as a variable, we have an I as a variable. So you do it exactly the same way. So I am just going to do one example and move on. So if you have 3 minus 2i minus, you have negative 2 plus 3i. Okay, I am subtracting two complex numbers. So if these were polynomials, if this was an x instead of an I, you would start by distributing the negative first to get rid of that negative and collecting the like terms, right? So let's do that. So we get 3 minus 2i plus 2 minus 3i. Okay. Now we collect the like terms, terms that don't have an I in it. So we get 3 plus 2 is 5. And then we collect the terms that have an I in it. So you add the coefficients in the front. Negative 2 minus 3 is negative 5i. And that's it. So there's really no magic to this. You just treat them as polynomials. And then you just add the like terms. Okay. So the next thing we're going to do is multiply complex numbers. Again, it's exactly the same as multiplying polynomials. So let's take a look at one example. So we have 3 plus 2i minus 2 plus 3i. So we are multiplying these two complex numbers. So if this was a polynomial, what do? We take each term of the first polynomial and multiply it by the second polynomial and do the same thing. So let's do that. 3 times negative 2 is negative 6. 3 times 3 is 9i. You just treat that I as a variable. 2i times negative 2 is negative 4i. And then 2i times 3i is plus 6i squared. Okay, so now we collect the like terms. So we have minus 6 plus, I can collect these I terms, so we get 5i plus, now here's where we're going to deviate. We do know I squared. Remember, we defined I squared as what? Negative 1, because I was square root of minus 1, so I squared is negative 1. So this quantity here is minus 1. So what is 6 times minus 1? So that'll be negative 6. So I can add these real parts over here, so you get negative 12 plus 5i. So multiplying complex numbers is exactly the same as multiplying polynomials, except for this little thing you got to remember. Anytime you have I squared, that is actually minus 1, so you have to replace that, because you don't want to have an I squared in your answer, because complex numbers are always written in this form, a plus bi. That's just a term with an I in it. Okay, and keep in mind, if b is 0, then that term is not even present. Okay. Alright, so that's multiplying complex numbers. The next thing we want to do is divide complex numbers. So this is very similar to the topic we covered in the section on radicals on rationalizing. It's exactly the same. Because in essence, if you have a complex number in the denominator, for example, let me show you two examples. If I have 2 plus 3i divided by 4i, or another example, I could have 1 minus 2i divided by 2 plus I. Now in both of these cases, if you notice, okay, I'm dividing both two complex numbers, but this I is technically a square root of minus 1, and so is this I. Can we have radicals in the denominator? What do we learn in the section on radicals? We can never have radicals in the denominator. So we have to do something called rationalizing. If you had something like this, if you recall, again, if I had 3 over square root of 2, when we just had one term with a radical in it, then we multiplied by square root of 2 over square root of 2. Okay, the reason for that is because we eventually wanted to get a 2 out of this. We wanted to get rid of that radical. So we did that because if you multiply by square root of 2 times square root of 2, we get square root of 2 squared, because you multiply the inside. So you get 2 times 2 is 2 squared. Now the power and the radical are the same. They kind of negate each other, so you get that 2. On the top you just get 3 square root of 2, so we get 3 square root of 2. There's your answer. So whenever we wanted to get rid of a radical, a square root, especially a square root, we just multiplied by the same square root again. That only applies to square roots. On the other hand, if we had a problem like this, if we had 2 over square root of 2 plus 1, now we have two terms, and either one has a radical or both of them have a radical. In that case, if you recall from section 1.4, 3, we multiplied by the conjugate. The conjugate was square root of 2 minus 1, square root of 2 minus 1. So I'm hoping you remember these two examples, because that's exactly what we're going to do with these. Because technically I is just a radical square root in the denominator. So we're going to do the same thing over here. We're going to multiply by I again, because if I want to get rid of a square root of minus 1, I'm going to multiply by another square root of minus 1, just like I did over here. And then square root of minus 1 is I. So we're really going to multiply by I. Over here, we're going to multiply by the conjugate, 2 minus I, 2 minus I. So let's take a look at those examples. So if I have 2 plus 3i over 4i. So I want to get rid of this I from the denominator, because that actually happens to be a radical. So let's do that. I'm going to multiply by I, because it's a square root. Remember, I is just the same thing as square root of minus 1. Because it's a square root in the denominator, to get rid of that singleton square root, you just multiply by the same square root again. And since square root of minus 1 is I, I'm going to just multiply by I. So on the top we distribute the I, because this thing needs to be, so you get 2i plus 3i squared. On the bottom we get 4i squared when you multiply that. What do we know about I squared? We know I squared is minus 1, so this I squared here is negative 1, and so is this I squared. So we get 2i minus 3, because 3 times negative 1 is negative 3, and on the bottom we get 4 times negative 1 is negative 4. So we end up with, now a lot of the time students will leave this as the answer, but this is wrong. Anytime you have a complex number, you always want to write it as a plus bi. You want the real part separate and the imaginary part separate. Right now, because they're both divided by 4, negative 4, they're like one chunk. We don't want that. We want to separate the numerator terms in the numerator. So I'm going to take 2i and divide by negative 4 minus 3 divided by negative 4. I'm just going to write this number first, because we always tend to write the I term at the end. That's just for looks. So we get 3i minus 4i is just 3/4. 2 divided by negative 4 is just minus 1/2 I. And there's your answer. I don't know why I have equalities here, but there's your answer. Okay? So when you do these problems, okay, just make sure you follow the same logic we did when we did radicals. Just remember I is really square root of minus 1, and just do that. Since there's just a singleton I in the denominator, multiply by the same thing to get rid of it. Then you can see we don't have an I in the denominator anymore, so we took care of that the I from the denominator. So let's take a look at the second example. We had 1 plus 2i divided by 2 minus I. Okay, so let's do that. Now I again have a I term in the denominator, which I cannot, because I is the same thing as a radical. So I need to get rid of that. Since I have two terms in the denominator where one of them has a radical, we do what always? We multiply by the conjugate. The conjugate of this term, this thing, is exactly the same thing, except with an opposite sign in the middle. That's the only sign we change. Since I'm multiplying the bottom, we also have to multiply the top. So on the top we have two complex numbers we are multiplying, so we'll have to distribute like we did in the multiplication of complex numbers example earlier. So we get 1 times 2 is just 2. 1 times I is just I. Then we get 2i times 2 is 4i. And then 2i times I is plus 2i squared, divided by, now here's where you have to use some of the knowledge that we've already accumulated in this class. Anytime you multiply two conjugates, what happens? If you multiply a minus b and a plus b, you have two conjugates, you end up with what? The square of the first term. You put a minus and you get the square of the second term. We always get that when we multiply two conjugates. So let's do that. What's square of 2? 2 squared is just 4. Put a minus in the middle. What's the square of I? I squared is just I squared. So anytime you're multiplying conjugates, remember that. You can take advantage of this. This is the formula for difference of two squares, just backwards. So now we know that I squared is negative 1, and I squared is minus 1. So let's clean this up a little bit. You have 2 on the top. These can be added since they have i's in them, both of them. So we get plus 5i. We got 1i plus 4i. 2 times negative 1 is negative 2, divided by 4. Negative times negative 1 is positive 1. The 2's will cancel, so we get 5i divided by 5. The 5's will cancel, so we just get I. So that's the answer for that problem. So we took a look at dividing complex numbers. Just remember that when you're dividing complex numbers, you basically are just doing what we did before with radicals. Okay, let me do one last example and then we'll move on. So let's say if I have 3 plus 2i minus 5 plus, I'm sorry, minus, let's do plus 3i. Again, I'm dividing two complex numbers because this is a complex number, has an I in it, so is this. Because I have complex numbers are the same thing as radicals, I have a term with a radical in the denominator, which I cannot. I have two terms, one of them has a radical. So what do? I multiply by the conjugate. So what's a conjugate of this thing? The conjugate of this is exactly the same thing, except the sign in the middle is different, just that one. So you get minus 5 minus 3i. We get minus 5 minus 3i. So we distribute on the top. We have this complex number multiplied by this. So 3 times negative 5 is negative 15. 3 times negative 3 is negative 9i. 2i times negative 5 is minus 10i. 2i times negative 3i is negative 6i squared. Divided by, what happens when you multiply two conjugates? Remember we talked about that earlier. We just get the square of the first. So what's the square of minus 5? Minus 5 times minus 5 is 25. Minus, we get the square of the second. What is the square of 3i? 3i times 3i is 9i squared. So now we know that I squared is minus 1. So let's replace those. And let's collect these two terms because they both have an I in it. So you get negative 15 minus 19i plus 6. On the bottom we get 25 plus 9, because negative 9 times negative 1 is positive 9, negative 6 times negative 1 is positive 6. Once again, I can collect these two terms because they don't have an I in it. So you get negative 9 minus 19i divided by 34. Once again, you might be tempted to say, oh, I'm done. But remember, with complex numbers, we always want to write the real part and the imaginary part separate. If I put them under one denominator, they are no longer separate. So we need to separate the real part. So you take negative 9 over 34 minus 19 over 34i. So there's your right answer. Okay, you always want to split up that numerator. Okay. And that's pretty much it with complex numbers. All you have to do is remember some basic properties of complex numbers, which is I is equal to square root of minus 1 and I squared is minus 1. And the complex numbers are always written in this form, a plus bi. They always separate the real and the imaginary part. And now from this point onwards in this class, we can handle square root of negative numbers. We just have to write them in complex form. Okay. And then we looked at some properties of complex numbers, not properties, some operations on complex numbers, adding and subtracting. That's just like working with polynomials. Multiplying is exactly like working with polynomials, except you have to worry about that I squared. And then the last thing to note is dividing complex numbers. That is just like working rationalizing, because that's exactly what we did with radicals, because a complex number, in essence is I is in essence is a radical. So whenever we have a complex number in the denominator, we have a radical in the denominator. So we want to get rid of that, and that process is called rationalizing. So that's what we did. So I showed you some examples. Make sure you practice the problems so that you can master these concepts.